Hello, I'm Madeline. This is Bruce, and that's Abby. And we might not be as interesting as the hood, but we are going to talk about photolithography. So, photolithography is basically when a mask is made, printed, and then light is shined through normally high energy light like UV or X-ray light, and that will create some kind of intricate design onto this chip. And the chip normally contains a substrate and metals and other materials that when different stripping and etching goes on, it will come out with a chip that can be used in computers and CPUs. And that is very important in today's day and age because we can use nanotechnology to try to make those masks smaller, which eventually makes those chips smaller as well, allowing us to have smaller phones and computers. And as we decrease the chip size, the distance between different components in the circuits also decreases. And this can be good, but then it also can increase the resistance because the wires can get thinner. So as developers make these new chips smaller, they have to take into account the proportions and that they eventually want to come out with the greatest power input.
Cool. So, Madeline, I'm not sure if I mentioned this, but the artist makes a really good analogy of using photolithography in baking a cake. So, as you can see, first you have to gather the ingredients and assemble them. In photolithography, what you're going to be doing is you're actually going to be layering things. So you're going to have a substrate, a conductive metal. We used copper in ours, but it could be any conductive metal or semiconductive metal, and then a photoresist. Next, you're going to put the cake into the pan. Or if photolithography, you're going to put a mask on it. And this mask will cover up the area that you want to be like the design or the wires. So that would cover that up, and then the cake goes in the oven. In the photolithography, your little chip is gonna go under UV light. The UV light will cause a chemical reaction to happen between the photoresist and all the uncovered areas of the photoresist, which makes it then possible for the next step to happen. So after you take the cake out of the oven, you're going to trim it. So you're going to let it up to cool, you're going to cut it up, and you're going to cut off all the burnt stuff. In photolithography, this is sort of the process of developing and etching away all the photoresist and the copper you do not want. So when you're cutting the cake, it's kind of like developing the design. So when you put your photolithography in a little thing, it will cause all the excess photoresist to fall away. And then you will then cut off all the conductive metal that you do not want because that will mess with your circuit. Finally, you ice your cake or you strip your metal. So then after you have a design, which is just metal and photoresist, you just need to take off the excess photoresist and you have your little wires. So lastly, you eat the cake, and this is actually when you use it. You may have noticed earlier, but the artist makes two cakes, one with like 3 little things and one with a lot of smaller things. So this is sort of talking about how we can use nanoscience to make these. So the smaller one is able to be eaten faster in 1 minute, as this person says, even though it's the same amount of cake. This is because when things are smaller and they have more surface area, as it always is in nanoscience, it's a lot easier to use. That's basically the process.
All right. So one limitation of this drawing, it is briefly mentioned, but it is not one of the primary features, is the need to use, in the case of the analogy, a clean baking pan, or with, in the case of manufacturing microchips, it's using like a clean substrate, because when you're looking at the scale that we're currently producing, which is on, like, the current feature size of most microchips is around 14 nanometers. So at that scale, even the smallest piece of dirt or contaminants will cause an immense problem when manufacturing. So we use a clean room, which is just a contaminant-free room where we can produce chips that have up to a 99.9% yield, meaning that 99.9% of the chips that come out of that clean room are useful. Questions?
So the big thing in making chips like this is resistance. And when the current has to travel a longer way, that is more resistance. So when it's a lot bigger, that's more resistance and it's slower. But the issue is when you're making things so small, the wires are also getting thinner, which also adds more resistance. So Madeline kind of touched on it, but it's finding a balance of making it small enough so it's faster, but not the wires can't be too skinny or else there'll just be too much resistance.
In addition to that, when you look at, once you get to very, very small features around the order of about 5 nanometers, you don't always have control over the flow of electricity through those transistors, so that can cause problems because if you can't control it, the chip is not going to perform the functions as it should.
The transistors do also get much faster as they get smaller.
Yes.
Okay, so I have a question for you. So now I get the question that I didn't ask last time.
All right.
Okay, so first, what is the mask in this picture? I think you guys said it, but
It's the
Cake
pan.
okay. So what key aspect of lithography is captured in this picture with respect to the mask?
That it takes the shape of the object or the pattern that you're trying to print onto the substrate.
Yes, but but other ones like with the picture and the other pictures, there was that concept was there, but there's a concept here that is pretty explicit with respect to a pan that hasn't been in some of the others.
Is it possible?
Tell me about your baking pans at home.
Well, I mean, we have
Stick
two
or
different
non-stick?
sized baking.
Stick or non-stick?
When you want to bake a cake, what do you do?
Oil it.
You just
Or the batter oven.
yeah, and okay, and you do the whole thing, and then you're done. And what do you do? And then when you're totally finished,
Get out of the pan.
you're totally finished.
Wash the pan.
Okay, and then after that,
Cake.
Use the pan.
reuse the pan. Okay, so what aspect of photolithography is captured really well in this picture?
You can use one mask over and over and over again to make multiple.
Of the same thing.
That's the key concept. The mask is really expensive to make, but you can use it again and again to make the exact same cake or the exact same pattern repeatedly. And that was the one concept that we had gotten before, so I'm really glad I waited until this picture came around. Okay, so now I have a second question. So the cutting off the burnt part is the stripping. What is the frosting? I'm sorry, I just can't figure out.
Actually, the cutting off the burnt part is the etching.
That was kind of one of the limitations of this drawing. I heard the timer, so I wasn't able to completely get into it. Is that obviously with these analogies, like you said, it's kind of hard. You don't really like ice the cake and then cut it off. So in reality, it's kind of the process is basically reversed. But that was kind of our this was like to the extent the analogy was able to explain the process.
So I guess I would say that basically the dumping the cake out of the pan is sort of the etching, because that's where you end up with the patterned cake that reflects the pan. And then, the little burnt part is the stripping. And then, I'm sorry, I'm afraid you might have to eat unfrosted cake. It doesn't taste as good, but...
I have an interpretation, and actually, also, I have an interpretation, and I like your team to maybe answer it. So relate the let's assume that the eating, right, the two figures in the bottom with the 1 minute suggestion of time, etc. If let's assume that the suggestion is that this is a function of the cake, meaning the value of making that cake is the cake itself, and maybe related to the icing. So would that kind of connection? Would you be able to say what might be the illustrator or the artist trying to say about the icing? What might that be related to your experiment?
Or not actually related to your experiment, but related to the process.
Or process, or how technology is used like this. If you add a layer and that layer is part of the function or a useful thing, like eating it tastes good.
Well, one thing that we looked at, and I'm not sure if this is quite the direction you're going, but when we were looking at lithography, we're also looking at other uses for it. So, especially with different methods like soft lithography of making actual nanostructures, where in order to make a specific structure, you make one little layer, and then you etch it out, and you make the pattern that you want, and then you put another layer on top of it, and then you etch that, and then slowly you can build up a full-size nanostructure.
Yes, so I think one interpretation of this is that the icing itself is one of the functional material structure that this illustrator wants to say. It could be, a structure of plastic, or in your case, perhaps the metal itself.
But a transistor is not just metal. It actually has multiple metals and semiconductors. So this could be more part of the